righty, good evening, everyone. Can everyone hear me? Good evening.
He's our new president. The assertiveness gene hasn't manifested itself yet. So,
I'm trying to ease you into it. We were going to try to keep the rituals to a minimum, but they said at least once. So you get one normal meeting. February, you're all mine. So this is kind of that transition period. Excellent. Very good. Well, welcome to your January 2026 meeting. I'm excited to be here. Thank you for selecting me to be your president. I hope to make that a decision that you don't regret. So, but really, it will kind of be the success of the club really isn't, it isn't up to me. It's really up to each and every one of you. So it's, your involvement really will be key. So I look forward to supporting what the club wants to do in the future. And I'm excited to see what we can do. Going back a little bit to kind of the year in review, we had a couple months of no meetings. So I'll kind of touch base a little bit on that and then talk about some of the things we've got going up, and then we'll move from there. Obviously, thank you to James and our hosts at the Kika Silva Pla Planetarium. We are blessed to have this facility to meetings. So thank you. And truly, we talk to a lot of folks at different astronomy clubs, and there are some that meet in planetariums, but we are among the blessed. So we appreciate that. A little timeline again. You'll hear me blab for 20 minutes or so. Hopefully I can get it down a little bit less than that. Then Orlando will give you a talk about when astronomy meets national identity. It's kind of a cool thing that he's been working on. We'll do our normal break. And then Dr. Cruz Aguirre will be doing his main presentation. So hopefully we'll be in for a good night. New members. We have a ton of new members. I know oftentimes the roll is called. There's 20 people on this list. So are there any new members here with us tonight attending their first one? Your names. Al Smith. Welcome. Thank you guys. So we're excited to have you here. The club is 237 members strong. I know that's the largest number I've ever seen. I don't know if you've hit that number before, but that's a really cool number to see. Do we have any guests that are here with us? Your name? Jim Herbert. Welcome, sir. Glad to have you. Excellent. On that topic, so everybody's a member for now, but your membership expires here at the end of this month, and renewals begin on the 1st. Especially for anybody, if you signed up for us in January, those new members, you were prorated, so that new membership kicks in on the 1st. These are the new rates that were voted on by the board. I think I sent out an email to, hopefully everybody got that in the first day or two of January, kind of mapping out what those new rates will be. We streamlined things a little bit to just make things a little bit easier to kind of spread out the cost that did go up. Some of the things that were taken into account for why the rates need to be changed. We know fully that rates haven't been adjusted in, as long as Wild Apricot would show us how long that's been, probably 10, 15 years. Astronomical League dues have gone up since then. Membership management, our system Wild Apricot, those fees go up. The size of our club puts us very close to another tier. When we trigger that tier, that cost doubles. So we really need to kind of maintain the finances as they are. The club's in a great position. We just want to make sure that it maintains that. Insurance costs, scholarships was something that the club started last year. I think universally that is supported by definitely all the board. We hope by all the membership is a really important thing we do. The state of kind of the world as it is with NSA funding cuts, that impacts some of the outreach supplies that the club has access to. Where once things were given away by NASA and other kind of the big clubs, Now clubs have to pay for that. So that's a cost that we anticipate bearing. And then just really in the last few years, the club just hasn't been able to really modernize with equipment. You've noticed we haven't done much out at Newberry Star Park, which is kind of our home facility. So we've relied heavily on our partnerships with Chiefland and the Deep Space Observatory. We're blessed to have that site there. Obviously, James and his team allow us to meet here at no cost. So really, our partnerships got us to where we are, but to move forward, those fees really kind of needed to be modeled. And really, we looked around the state of clubs in our area to see what are you doing, how are you keeping pace with costs, and really we kind of aligned ourselves to really that median level of what other clubs are. Some are higher than us, some are lower than us, but we really wanted to try to keep it as low as possible, but still give ourselves opportunities to improve the club and to provide more resources to the membership. So that's really kind of the bad news. I do want to remind everybody all the things that the club has available to you as a member. As a member of the Alachua Astronomy Club, you are by default a member of the Astronomical League. That's that quarterly magazine that you get. They have all kinds of observing programs that we'll talk about more in the year for anyone new. For anybody who's been here for a while, you're certainly familiar with those. Obviously, our monthly member meetings, those include 4 planetarium shows that are the same ones that this facility charges for. So those tickets alone are your membership, and just all the other things we do, from the outreach opportunities to kind of give back to the community, to just all the observing sessions we do. So just kind of want to provide what we're trying to keep going and build upon. Something new that just came in, and it's actually available today. So if anybody's familiar with Dwarf Lab, they provided me with a pre-production model of their Dwarf Mini telescope. I was required to do some testing before I could release it to the club. That testing period has ended, so it's now here. So the pictures you see on the screen were taken with this little guy. It did have the benefit of traveling with me out to Oklahoma, so some of these images were captured under Bortle 1 skies, but the same amount were captured here in my backyard at Newberry. The picture of the Triangular Galaxy is about 40 hours, both visual and dual band, stacked. But it just shows that something that can fit in your pockets can do stuff like that. So, and whoever wants to take it home tonight, see me at the break. We've got the whole kit here for you. Another thing that just came in the mail is the C-Star S30 Pro. I don't have that to give to you tonight. I'm testing it now. Those obligations are taking place now. I just got it last week. It was out with me at Chiefland this last weekend, so been able to do a little tiny bit. I have a little bit more work to do with it, but that soon will be added to the members loaner library. So hopefully you'll be able to get that as a borrowed telescope before any pre-order ships. So kind of hoping to highlight some of that. Some of the past things that we've done, the Far Out Journal Club, if you didn't get a chance to see that episode back in December, it was a hoot. It was a great episode. That is posted on our YouTube channel, so if you'd like to watch it again or catch it for the first time, please be sure to see that there. Our YouTube channel is just Alachua Astronomy Club, but if you just search for Alachua Astro, that should take you there as well. Previously, back in December on the 20th, we did a great outreach event at Hickory Ranch, and I was probably the most proud of this club that I've been, because we had 25 registrants participate in that event. So we had a really, really awesome turnout. I think we had, did they ever tell us the number of folks? I think the gentleman said in the evening it might have been between 150 and 200 folks. So it was a great night. Thank you for everybody who came out. If you didn't come out, we look forward to seeing you a little bit later. I'll talk about our January and February meetings here in just a second. Rosemary Hill, we had a couple different events out on the 15th. We helped with UF's astronomy department and had supported their open house. So you'll see some members there. And then on the 22nd, we also had our own private observing session, thanks to Dr. Reyes, who is in the back. So thank you, Francisco. We appreciate you allowing us to come out. December 13th, we had a great night. Lots of new members there. It was exciting to see some fresh faces. And it was also the peak of the Geminid meteor shower. So these are a couple of pictures. The one on the right is one that I took while we were out there, but on the left you'll see, I'm going to guess, I don't see, I haven't seen Andy, but if you're into meteors, and he uses an all-sky cam system to track meteors, so I'm going to guess it's kind of the Super Bowl for meteors. So he captured just loads of them throughout the night, so it was kind of cool to see that composite. Here just recently, this last weekend, we had a great night to see Dr. Hennig opened up the Chiefland Astronomy Heritage Museum for us, did a little bit of a presentation, and then had some great viewing. The scene was actually spectacular that night. So it was really fun to see. So if you have not been out to Chiefland, we encourage you to head out there. It's just about an hour from here. I highly recommend you join us at one of those events. We, of course, had our holiday party on December 7th. Thank you for bearing with me, those of us that attended the event. We had our fairly successful game of Family Feud. The cheating was kept to a relative minimum. We're not going to... I won't call anybody's names out, but I heard there was some shenanigans afoot, and on a personal note, I was actually really offended because I felt like I was outdressed. I went out and got the highest quality blazer I could find from Amazon. I grew out my beard and mustache, but then James comes in with the matching suspenders, so I think he wore it better, and then and then I had to be one-upped by my eyebrows. So you try, but
It works.
I mean, you did win it. You did wear it better. That's all I have to say. So
A little dolly.
it definitely, you need to twist it up a little bit. So, but hopefully this just shows if you didn't come, if you haven't come out to events, we try to have a hell of a lot of fun. So please.
And she said that. You didn't see that.
To come. Marianne alone is worth the entertainment. So that was the past. What are we doing here soon? Unfortunately, we had an event scheduled for January 17th. For circumstances that I won't get into too terribly much, we are forced to cancel it. It doesn't look like it will be rescheduled, but we do have an event coming up in February. It'll be very similar to December. We hope to have just as strong of a turnout from members. If you have equipment, great. If you don't have equipment, great, still come. Hopefully it was enjoyed by everybody. I'm excited to see the newer members that have come that have talked about wanting to do this more. I think that's really an important thing of what we do. Dave will be going out here just about a week from now over to Oak Park Village, which is a small community really near Celebration Point. He'll be showing some sights to the kids. While it is kind of a light polluted area, about as downtown as you can be in Gainesville, they're going to use some smart scopes, I believe, and do some visual. I don't think he needs any support as far as equipment's concerned, but if you want to attend and show up, you're certainly more than welcome to come take a look and talk about the stars with some kids. So we're excited for that. A little bit more personal to me, one of our other partners that we talked about previously, those partnerships, the Village at Gainesville, it's where I work. I think that's pretty well known. They provide those facilities to us for free. The holiday party, the facility cost us nothing. We held an event earlier where Dr. Hennig gave a great talk kind of about beginner equipment and kind of that selection process and some guidance behind that. So we just kind of want to, as a club, thank the residents and the community for allowing us to use their spot. So we'll bring some equipment out. I know I think we've got about 9 folks that are signed up for it. Again, if you have equipment, great, bring it, especially visual. Do keep in mind though that it's A lot of the seniors that are there are vibrant, that are absolutely mobile, but we do have some folks that have some mobility challenges. So don't bring your 6-inch dot that we're going to have to kind of crouch down for. So kind of keep that in mind. Binoculars, great. Again, just coming out and being part of it. I think you'll really, if you aren't familiar with senior living or have a preconceived notion of what senior living is, I think you'll be rather surprised. These are some of the most interesting people, and I guarantee you we will educate some folks, but I promise you'll probably learn some stuff as well. So not a day goes by that I don't enjoy that. That's really what keeps a lot of us going back day after day. So with that in mind, please make sure to register. It is a gated community. I need to get you on the list so that you'll go back. It's not a problem once you get in there. Even day of, give me a call, shoot me an email, let me know. I can get you back. It's not a problem. Anybody that does have equipment, fully understanding that it is a work night, if you want to bring equipment ahead of time, reach out to me, let me know. I've got my locked office. I've got lots of secure places that you can bring your stuff early. If you want to even bring it this weekend, I'm there on Saturday morning. Leave it. I can keep it protected. And then Thursday, you can just come from work or whatever you may have going on, if that's helpful for anybody. Coming up next, out at Chiefland, we will be doing an event on the 7th, kind of that similar scenario. If you've been to Chiefland, you know the rules, no white lights, kind of park on that south side of the road. If you haven't been there, we strongly encourage you, please arrive before sunset, about an hour, just to get acclimated with the site. It is a serious observing field. We want to be respectful from not just the homeowners in the area, but those that come out. We've got folks that travel, from all over that come to that facility to observe, to photograph. We really just want to be mindful of our lights and be the best stewards and representatives of the club that we can. So that being said, not to be serious, it's a lot of fun. Please be sure to come out, and then we'll let you know here around noon or so on that day how we look on that. Some other things kind of in the area that I wanted to make sure to highlight. Embry-Riddle, I know David talked about it a time or two before, has a thriving astronomy department. So they've got a lot of things going on, really about once a month, kind of in the winter. They have almost now dueling events. I guess they're more partnering than dueling. But they've got a great astronomy open house, but then also at the same time that evening, you can pop over to the Museum of Arts and Sciences, catch a show, but then also pop back over. Their students are out. They've got all kinds of clubs they're doing. We had instant ice cream that was made. They do bake sales. They also bring telescopes and observe. You can look through their meter scope on the roof of the building. They've got all kinds of great Takahashi telescopes. So they've got a great facility. If you haven't gone, I encourage you to go. If there's a group of folks that would like to go and carpool, I know a couple of us went out, I think it was earlier, I guess it was last year now that it's January, and I think we had a great time. So a great method to reach out to folks in the club, if you don't know, is groups.io. That's that kind of messaging platform. If you get an email from somebody going, well, how the heck did they get my email? As a member, most everybody is kind of signed up by default. I'm excited to see that more and more folks have kind of been sharing some photos on that. So it's cool to see that there's a little bit of life going on that. So if there's a group that wants to gather and head out, I think that'd be a lot of fun, and you'll definitely enjoy it. The Winter Star Party is a great event, and it's coming up here just the next new moon. So I think 5 weeks from now, it's down in the Florida Keys. I went for my first time last year. I know you'll see some other familiar faces. I believe the Haldemans will be there this year. I don't think they're with us tonight, but you'll see some familiar faces. Unfortunately for them, I'll be one of the presenters, so you have to hear me blab here. You don't have to hear me blab down there, but I'd be excited to see some friendly faces from the area go down there. And it's just a great opportunity to still be in the state, but also see some of those really cool southern targets. This in the bottom right is a picture I took from feet from my campsite. The telescope's featured above. And you can see the Southern Cross that's highlighted. You can see Carina will rise just above the horizon. There's the coal sack, the jewel box. So there's all kinds of those southern targets that we can't quite see from here that do kind of peak above the horizon deep into the night. So it's a really fun energy. If you've been to some star parties, they all have their unique personalities. This one is kind of got a Jimmy Buffett feel to it. So it's a fun event. And then I wanted to make sure to highlight some of the photos that I've either been sent or seen that have been contributed by our members. I think at the Paynes Prairie Outreach, Oren, one of our brand new members, I've never met him before, was imaging down at the end. So these are some of the pictures that he took actually at the event that night. So doing outreach and imaging. So that was exciting to see. This awesome photo, I hope it shows up as well. Oh good, it kind of does. This wide field view that Orlando took. Were you out at Chief Linden? Was this the December picture?
No, this
Oh, that was this weekend? Oh, wow, you're on top of it. So a really cool view of Orion. You can see M42, the Horsehead, the Flame. This is the Barnard's Loop. You can see, gosh, M78. Even the Witch Head is kind of up in here. So that's a great photo. I'm excited to see what you do if you get some more subs on that. But that's just an example. You were unfiltered at Chief Linden for 100 minutes. So it's worth the drive out. It's a really cool place. And then Alex, one of our new members as well. I think he's been to the last two meetings. He and his wife have come out and spent some time with us. So these are some of the images he shot with his Red Cat 51 out at Chief Linden. I know. I think these are from December. We were fighting clouds pretty on and off, so it was a great night for the meteor shower, but the clouds were certainly making themselves known and still able to capture some of that. So that's a really gorgeous shot. I wanted to make sure to highlight some of the things coming up. In case you didn't know, Jupiter was at opposition here over the weekend, so it is the closest to us in its orbit. So it's as bright as it'll ever be. We had phenomenal seeing, but just because it was at opposition on the 10th doesn't mean it's still not in the neighborhood right now. So if you head out and see that Jupiter looks a little bit brighter, that's why. We are coming up on a new moon weekend, so it's a great opportunity. We kind of are in that prime season to see the sky without some moon. January 23rd, you'll see a Saturn and Moon conjunction right around 7 o'clock. If you look to the west, you'll see Saturn kind of get pretty close to the moon. And then obviously it's January, so of course winter is here. You can really start to see the winter hexagon really start to take a prominent part in the sky. So get out there and make sure to look up. Does anyone have any announcements or things that I may not have covered? No? Jerry, do you need any support on the 24th down in Ocala?
I think we will. We'll probably need like 3 dogs and 2 smart scopes. I'll bring 1 smart scope. So we're going to be looking at the Ocala Wetlands Recharge Park. We're going to have a tour before sunset of the park, and then after sunset, we're going to just show you some of the night sky.
Gotcha. So for those on Zoom here on the 24th, Jerry and a couple club members will be down at the Ocala Recharge Wetland Park doing some outreach and whatnot. So looking for a few smart scopes and looking for a few larger aperture Dobbs and whatnot to help out. So if you're free on the 24th and want to help out, we'd love to see you take part. Well, I think I've punished you long enough. So I think I've got Mr. Orlando now up to talk about when astronomy meets national identity.
Oh, I need.
Oh, yeah.
Fuzzy thing fell off the end of that.
Oh,
This is a wind screen, so
can't view that. You are muted right now.
I need to flip this around. Get that properly. Okay. There we go. Okay. Now, let's see. 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 Let's see.
Testing. Okay, everybody hear me?
And it's unmuted, right?
You were muted. Yeah, just
Did you see the little switch on there to unmute?
on your path.
Okay, now.
Okay, we're good now. Welcome to the first Members Corner of 2026. Woohoo! My name is Orlando Barris. I am the new programming of director here for the Alachua County Astronomy Club. That means that it's my job to get you to come stand up here where I'm at right now. This is a space that's reserved for you. It's for you to come here and talk about an astronomy topic that you're passionate about. You don't have to be an expert. You don't have to be an astrophysicist. You just have to go out, research a topic, and come and present it. It could be a YouTube video you watch. It could be an article you read. Or you just want to get something off your chest. If it's astronomy related, we'll take it. And if you need help selecting a topic, just come talk to me, and we can brainstorm some ideas. Okay, so to the presentation. When astronomy meets national identity. When most people think of astronomy, they think about telescopes, observatories, space probes, deep sky images. When you think about national identity, you think about politics, history, wars, national anthems, and national flags. Astronomy feels like it should be timeless or detached from these sort of earthly concerns. But tonight I want to show you that the sky has quietly found its way into national identity. Sometimes it's symbolically, sometimes it's metaphorically, and in one case, it is scientifically. But before we get there, I just want to show you a few national flags that sort of work that theme into them. A group of nations in the Southern Hemisphere share a recognizing celestial symbol, the Southern Cross. Those are Australia, New Zealand, Papua New Guinea, and Samoa. Yeah, I need a little bit of light, thank you. Just a little bit, you can still see it, right? Okay, and we are missing Samoa. The Australian flag opts for the seven-pointed Commonwealth star that represents the 7 federated colonies of the British Empire, with the exception of Epsilon Crucis, which remains a 5-pointed star. The New Zealand flag shows the Southern Cross with a regular 5-pointed star, and has been used to represent New Zealand and other Southern Hemisphere colonies since the early days of European settlement. In native Maori, the Southern Cross is identified as Mahutonga, which means aperture in the Te Ikaora, the Milky Way. So it's an aperture that brings on all the storms out of the Milky Way. The nations of Samoa and Papua New Guinea have decided to adopt the Southern Cross as part of the national flags once they achieved independence from their European colonizers. So you can see there is this strong sense of Southern Hemisphere identity, of home among these nations. And this is all represented by the Southern Cross. Then we have a group of nations that use the star and crescent moon motif. These are Pakistan, Malaysia, and Turkey. Now, these do have ancient astronomical roots, but they function primarily as religious or cultural symbols, not celestial representations. So you see that across the world, astronomy appears mostly as a metaphor, the idea of identity, the idea of home. And now we come to the one country who is said to have the most scientifically accurate flag in the world. This country, of course, is my home country of Brazil. I miss the turkey flag. I put this painting here by artist Pedro Bruno because it just looks so cool. By the way, most scientifically flag is a category that we created for ourselves for which there are no other contenders. Brazil is the only national flag that is an actual star chart. So it's not a symbol, it's not a metaphor. This is the actual sky in the Southern Hemisphere. And this is where astronomy and national identity fully collide. So let's work our way out and then move towards the center. The color green is associated with the, I'm sorry, I forgot to show you this. This is a picture that my brother sent, just a panorama of the sky. So you can see the Southern Cross right there in the middle, and then you have Triangular Australia and Canis Major to the left. And here we have them placed off. All right, so the color green. The color green represents the House of Braganza, that was the Portuguese royal family. The first emperor of Brazil, we only had two, was one of the many sons of the Portuguese king. Later, the color green came to be associated with Brazil's many forests. The yellow color is associated with the House of Habsburg. That was the first empress of Brazil, Maria Leopoldina of Austria. Today, the yellow color is understood to be sort of the mineral wealth of the country. Across the middle, there's a motto, Ordem e Progresso, literally, order and progress. That is sort of comes from positivist philosophy of the 19th century and is represented by French philosopher Auguste Comte. And the quote goes, love as a principle, order as a basis, progress as the goal. They didn't include the love part, which is kind of disappointing. And then you finally come here to the middle. Now we have this blue circle. Now this blue circle is actually a sphere. It is a celestial sphere. And we're looking at it from sort of like an outside perspective, as if you could look down on the celestial sphere. So the constellations are actually flipped from what you see from the ground. Right down there at the bottom, you see that tiny star, that's Sigma Octantis. That one lies 1 degree from South Celestial Pole, almost in direct opposition to Polaris. So, you know, it's a globe, and you're looking at it not from an equatorial perspective, but sort of from below, from a southern perspective. So the southern hemisphere dominates the celestial sphere. So here we have the Southern Cross right in the middle, Scorpius to the right of the cross, but in the real world is actually to the left of the cross. Canis Major on the left, and then we have Canis Minor represented by the single star Procyon. Triangular Australia is between Scorpius and the Southern Cross on the right. Carina is represented by the single star Alpha Carinae. The octants are represented by Sigma Octantis, that's the tiny star I mentioned earlier at the bottom of the world. And then Hydra is represented by Spica at the top, above the banner, and that's Alpha Virginis. And that's the reason that's the only star that appears above the banner, but I'll circle around to that later. Just like the American flag, each of these stars represents a different Brazilian state and the Federal District of Brasilia, capital of Brazil. That's why not every star in every constellation is represented. We only have 26 states plus the capital. Now this goes further because the position of the constellations marks a specific moment in time. It shows you what the sky looked like over the city of Rio de Janeiro in November 15th, 1889 at 8:30 p.m. This is when Crux, Southern Cross, is crossing the meridian over the city of Rio de Janeiro, so it's in this upright position. I told you that Brazil only had 2 emperors, and this is where we got our first president of the republic. It's Presidente Deodoro da Fonseca. He just happens to be from my home state of Alagoas, up there in the northeast. On the flag, Alagoas is represented by Shahula, or Lambda Scorpii. Lambda Scorpii is 570 light years from Earth. It is a blue subgiant in a triple star system. It is the second brightest object in the constellation of Scorpius, right in the stinger. The original capital of Brazil, up until the 1950s, was the city of Rio de Janeiro, located in the state of Rio de Janeiro, represented here by Mimosa or Beta Crucis, which is at a distance of 208 light years and is a blue giant type star, extremely hot at 27,000 Kelvin. I'm not going to go through every one of these. I just want to give you the highlights because we don't have a whole lot of time. São Paulo is home to one of the largest cities in the world. It's the city of São Paulo, state of São Paulo, and is represented here by Alpha Crux at 320 light years. This is a multiple blue-white star system, and it's the brightest star on the Southern Cross. So that's Alpha Crux. The state of Amazonas, which contains most of the Amazon forest, is Procyon, or Alpha Canis Minoris. This one is at 11.5 light years from Earth. It's a binary system, and a yellow-white star and a blue dwarf. It is one of the brightest stars in the sky. It is one of the nearest bright stars to Earth. The state of Goiás is represented by Canopus, or Alpha Carinae, and that is a bright supergiant. This is the second brightest star in the entire sky. The state of Pará is represented by Spica, or Alpha Virginis, at 250 light years from Earth. This is the only one above the white band because part of the Brazilian territory does lie, in fact, in the northern hemisphere. So that sort of representing, the northern hemisphere section of Brazil. The equator line cuts right across the middle of the Amazon right there. State of Bahia, State of Bahia, where Portuguese explorers first landed in April 22nd, 1500, is represented by Gacrux, or Gamma Crucis. This one is 88 light years from Earth distant, and it's a red giant star. This is the closest red giant to Earth that is visible to the naked eye. I am getting all my slides mixed up here, but that is Gamma Crucis. The state of Mato Grosso, which also has a decent chunk of the Amazon rainforest, is represented by Sirius, or Alpha Canis Minoris. This is a close one, 8.6 light years, and also visible from the northern hemisphere. This is a main sequence A-type star with a white dwarf companion. Sirius is the brightest star in Earth's night sky. And finally, the current capital of Brazil itself, Brasilia. Brasilia is a city that was designed and built from the ground up all at once in the 50s and 60s. The federal district is represented by Sigma Octantis. This F-type giant star is about 280 light years and is crucial for southern navigation. But it's only at a magnitude of 5.4, so it's only visible in very dark skies. Sigma Octantis lies 1 degree from the south celestial pole. So not quite a polar star, but very close. The Brazilian flag reminds us that astronomy is not isolated from culture and can indeed shape national identity. It also reminds us that the night sky belongs to everyone, not just scientists. Brazil chose to mark its republic not with weapons or animals or rulers, but with the universe itself. So the next time you see a national flag, you might ask, is it just color or cloth, or is there a deeper story written into it? In Brazil's case, the answer is written on the stars. Thank you.
Well, it's a little weird because as the head of programming, Orlando picked our year token out, so kind of weird to send him home with it. So I'll at least do it. But this year, keeping with our money theme, we have an uncirculated 2025 Vera Rubin quarter. So we want to make sure that we're a small astronomy club, but at least the pay's not great, but it's more of the thought that matters. So, but thank you so much. We appreciate it.
Thank you.
Excellent. Well, I think that's it for the first half. It's time for some snacks. As usual, please keep all food and drinks outside of the planetarium. We'll be back here in about 15 minutes. Call it, let's see, about 5 till the hour. So, but we'll come wrangle you. So feel free, please welcome our guest speaker and our new members as well. So thank you guys. All righty, everybody. We'll kind of give it a 30-second warning for anybody that's straggling from the outside to come on in. While we've got some folks walking in, does anybody have any plans for like the New Moon weekend? Is anybody going down to the St. Pete Club? They've got their party going on this week. It actually, yeah, I believe it starts on the 14th and runs through the 18th. So you're stronger than I am because the weather Thursday night looks Arctic.
Oh, Arctic. Florida, you got it.
Hey, I grew up in Ohio, so I'm familiar with cold, but I've lived here long enough that my cold tolerance has gone out the window. So I remember growing up, and we had some family move down where I used to make fun of them for that, and now I'm that. So I guess I'll take the pokes. So looks like I think we got most everybody back in. So tonight we're pleased to welcome Dr. Fernando Cruz Aguirre. He is an assistant scientist at the University of Florida in their Department of Astronomy and a member of the Hoadley Ultraviolet Space Lab. His research focuses on how ultraviolet and high energy radiation from stars shape exoplanet atmospheres and their potential habitability. Please correct me if I'm wrong once we are fully introduced. He earned his PhD at the University of Colorado Boulder, where he worked on Hubble Space Telescope studies of dwarf stars and led the Sistine Ultraviolet Sounding Rocket Project. He also participated in NASA's Astrophysics Mission Design School, contributing to a next-generation ultraviolet mission concept. At UF, he works on new UV instrumentation and mission development, including the UVIA CubeSat and CRAFTS sounding rocket. Please join me in welcoming Dr. Fernando Cruz Aguirre.
All right, how is that? Everyone can hear me? Good, awesome. Okay, so thank you for having me here tonight. Thank you to the organizers for inviting me. I had a lot of fun putting this talk together, and I hope you enjoy it as much as I do. So let's see. We can get this. There we go. Okay, cool. So yeah, I'm going to be talking today about the role of X-ray and ultraviolet light and how that can impact the habitability of exoplanets. I wanted to start off by asking, oh, that's interesting. That's a smaller font size. So we'll see how that plays out. I don't have too much text on here, but we'll see. So I wanted to start out, if I were to ask you what you think the building blocks of a habitable world would be, what would they be? And feel free to just shout out. Water, yep.
Oxygen.
Oxygen is very important for us, yes. Carbon. Nitrogen, yep.
Heat.
Hmm?
Sun.
Heat, yes, the sun. Sun's very important, yep. Any other suggestions?
Water.
Mm-hmm.
Clear skies for astronomy.
Clear skies is very important, yes. You can't study the magnetic field, yes. Carbon, yep. All right, awesome. Those are all really great. So oh, interesting. That text is the right size. Weird. All right. So yeah, I had put a few things here that I figured you might have guessed. I heard a lot of carbon, nitrogen. Those are all very important. Carbon, hydrogen, oxygen, nitrogen constitute most of our biomass here on Earth. Phosphorus and sulfur are very important for our DNA. Magnetosphere, I had heard. Having a rocky surface is pretty important for us, so we can actually, have a surface for life to originate from. And then I have a list here of things that you might not have thought about, like the type of star that you're orbiting. How variable is that star? How much metal is in that star? What is the mass of your planet? That's going to have a big impact on habitability. Are there nearby planets? Do you have a big Jupiter-sized planet right next to you, preventing you from actually forming into a planet, like our asteroid belt? How eccentric is your orbit? Are you very circular like the Earth? Are you just super eccentric like Pluto? You're going further out of the orbit of Neptune and then back in. There's lots of these other little things that go into habitability, including where we are in the galaxy. If you're too close to the center of the galaxy, you're going to get blasted by all this high-energy radiation. Whereas where we are, kind of in the outer parts of the galaxy, it's not too bad. And I don't have the time to talk about all of these things today. There's just too much to go over. But I did want to touch on the spectral type of the host star and how that can impact things like how much liquid water is in our atmosphere and whether or not we even have an atmosphere to begin with. So I wanted to start with what is high-energy radiation, talking about what that is, how we observe it, and things like that. We're then going to go into what is photochemistry and how that relates to habitability, how photochemistry actually affects planet atmospheres, and we'll wrap up with how do we actually observe this out in space. And so to that first point, what is high-energy radiation? This is radiation that is at ultraviolet wavelengths or at higher energies. If you asked a gamma ray physicist, they might give a different definition of what high energy is, but you have an ultraviolet astrophysicist tonight, so this is high radiation, or high energy radiation. You can see here on the right some beautiful images of the sun that was taken with a space telescope in various different wave bands. We have visible light, ultraviolet light, and a few X-ray bands as well. And here is our wonderful electromagnetic spectrum with some units representing the wavelengths of these lights. So we have X-rays all the way to the left, the extreme ultraviolet, the far ultraviolet, which is what I spent a lot of my time on in graduate school, the near ultraviolet, the R kind of went down a little bit, that's okay. Of course, our visible range, and then the near infrared at higher and higher wavelengths. We like to sometimes categorize the X-ray and extreme UV together into something we call XUV light. We'll talk about why that is later on. And you might have heard about UVC, UVB, UVA light, rather than near and far UV. These are types of UV light that will give us UVB is responsible for sunburns, UVA for suntans, and that's why we gotta wear our sunscreen, especially here in Florida, to protect ourselves from these higher energy wavelengths being emitted from our sun. You don't really hear too much about UVC, and we'll get into that in just a bit as to why not. So here I have on the right is a figure of the high energy radiation of our sun in that same kind of bands that I had shown before. We have the near infrared over to the right. The visible light, of course, is where the light from our star peaks. That's why we see in the visible. And then we have the near ultraviolet light, which starts coming down. This is what we would call our solar continuum or black body radiation. It's the light coming off from the surface of our sun, the photosphere. And you might think, okay, if we were to continue that trend downward, far ultraviolet light will just keep getting weaker and weaker and weaker. And we don't quite see that. We do see that there is a bit of extra far ultraviolet light that we might not have expected. And there's also these interesting spikes here. These are emission lines that are coming off of the higher atmospheric layers of our sun. And then you might think, okay, well, maybe something like that will happen again in the EUV. And that's where this trend just completely breaks. And the sun actually has a surprising amount of X-ray and extreme ultraviolet light that it's outputting. Now, to be fair, it is 1/millionth as much as the sun is outputting in the visible range. The y-axis here is a logarithmic scale. So although they kind of look close in this plot, it's a million times brighter in the optical than in these X-ray and EUV wavelengths. This is what we would consider the high energy radiation, as I said before. X-rays all the way to the near ultraviolet. There are some of these features in there kind of buried in the solar continuum. And we also call this dynamo-driven radiation. And that's because as we understand it, this type of light comes from the solar dynamo. What happens is you have our sun here up on the top left. It has these magnetic field lines that it generates through its dynamo. And the sun, like other stars, does not rotate the same way that our Earth does. The equator actually rotates faster than the poles do. And this will twist up these magnetic fields. And all of this twisting of magnetic energy actually heats up the upper layers of the atmosphere of the sun, causing this high energy radiation that we might not have expected otherwise. So in this figure here, I'm showing the transmission of our atmosphere at these different wavelengths. So you can see the visible from space reaches all the way down to the surface of our planet. There's some interesting gaps here and there in the infrared. There's a nice big gap in the radio that lets us do radio astronomy from the ground. But if you look over to the left, you'll see that the UV and X-ray light is completely blocked off. The upper layers of our planet's atmosphere actually absorbs all of that light, and it isn't able to reach the ground. So the only way to really observe this type of light is to go into space, like we have with the Hubble Space Telescope. NASA has also launched the Chandra X-ray Observatory to explore higher energy forms of light. And the European Space Agency has also put out the XMM Newton Space Telescope to study this kind of light. These are kind of the big three telescopes that we have. These are what we call our flagship telescopes. They are built for the community. Any astronomer can propose to these to do all types of astronomy. So it's a very shared, very powerful, it has to do it all essentially. But there are many other missions that operate in this bandpass that are smaller in scale, smaller in cost as well, and they're a bit more specialized. Here's just a sample of these. It's not a complete list, but some pretty relevant ones, as well as the Sistine sounding rocket that I worked on. But we have things like the NICER mission that's on the International Space Station, XRISM, which is a joint X-ray telescope between JAXA, NASA, and the European Space Agency. AstroSat is a very interesting one that it actually images both in the X-ray and ultraviolet at the same time. And you'll see right in the middle there, that EUV bandpass, there's one single space telescope that we've really had in that regime, the Extreme Ultraviolet Explorer, which has not operated for the last 20, 25 years or so. So that's kind of a starved area in our electromagnetic spectrum. We haven't been able to do a lot of research in that region for some time. But that is changing. There are a few missions here that are upcoming. They are funded and they're actively being built or about to launch. I actually found out this morning that the Spark satellite here is no longer a proposed mission, it is now in space. So that's really cool. And then we have this Mantis CubeSat, which will be the first time we'll be visiting EUV wavelengths since the early 2000s. So that's going to be a very revolutionary spacecraft that is the size, let's see, what do I have here? It is probably the size of this. Little spacecraft doing really big science. And we have several others that are currently in the proposal stage that are being proposed actively to NASA, as well as some other space agencies as well. The Canadian Space Agency has one called CASTR that is quite similar to the Hubble Space Telescope in some of its capabilities. And there's some here also in the EUV bandpass, such as the Craft sounding rocket that I led the effort for that type of mission. You can ask me about it later if you're interested. But we have lots of missions. Lots of these smaller ones are more specialized to different types of science. These are all kind of in the realm of exoplanets. Oh, okay, great, thank you. Here we go, cool. Cool, okay, so high energy radiation and how we observe it, great. Let's now talk about photochemistry, which is a little bit scary, but hopefully these very fun PowerPoint animations will make it a little bit easier to understand. So the definition of photochemistry, first of all, defined by Nature Scientific, is photochemistry is the study of chemical processes that are triggered by the absorption of light. So in this figure here, it starts out with this UV light coming from the host star of this exoplanet. It interacts with the water molecule and splits it in half, essentially. Well, 1/3 and 2/3. But then these broken pieces can then go on to interact with other molecules in the atmosphere. And you can eventually follow this chain down to turn hydrogen sulfide, for example, into sulfur dioxide. And once this happens over and over, you can change what's in your atmosphere over time. An example of this happening on our planet is in the ozone layer. Far and near ultraviolet light are pretty good at breaking apart oxygen molecules into their atomic form. And then these can further interact to form ozone. And then on the right here, we have near ultraviolet light is very good at breaking ozone apart. And that then splits it up into atomic and molecular oxygen. And then this cycle kind of just repeats and repeats and repeats in our ozone layer, breaking it apart and reforming it again. So there are a few different types of these, what I call photochemical triggers, that start off these chain reactions of chemistry within atmospheres. The first of these is photoexcitation. So we have a very humble oxygen atom here, carbon monoxide molecule over there. And if you were to hit it with a photon, ooh, the animations are, okay, this will be fun. So if you were to have the yellow squiggle there is a photon of light. If it were to hit this molecule or this atom here, it will kind of absorb that photon, gain a bit of energy, and then it can spit that photon back out into some other direction. And those photons can then go on to interact with other things. For our molecule on the right, we can have it have a photon come in, and it can actually shoot out multiple photons in different directions of lower energies. And then those photons can go out into the atmosphere and interact with other things. This is a process that happens, for the example of oxygen, this happens in our upper atmosphere. It's very rich in oxygen atoms. And UV light from our sun will actually excite these oxygen atoms and have them absorb this light and then re-emit it into other parts of the atmosphere. We have then photoionization. It's a similar process, but rather than spitting out a photon, it actually spits out an electron, and then leaves behind a positively charged either an atom or a molecule. And then that green dot, the electron, would then shoot out at fairly high speeds, and then it can bounce around and do other things in the atmosphere. This is a process that happens in the ionosphere of our planet very often. We have the third one, photodissociation. What this means is to essentially break these molecules apart, like I had shown previously with the example of oxygen and ozone in our atmosphere. You can take these and split them apart. The animation's not playing, but if you imagine it splitting apart, that's what it would do. And same thing for the water molecule. And the last one, it's a bit of a weird word, photodesorption. If you can imagine a grain of dust, if you will, having a lot of different molecules on its surface in a solid state. So this is frozen hydrogen cyanide on the surface of this dust grain, and this happens in protoplanetary disks, the birthplaces of planets. You can have this high energy radiation come in, and it can actually lift off I guess it doesn't want to lift off today. That's all right. But you can imagine that these molecules can absorb light, and then they leave that dust grain, and then can go interact with other parts of this disk. So, high energy radiation we've covered. Photochemistry, we've talked about different ways that photochemistry can occur in atmospheres. And now we want to talk about what that actually does. I showed this plot before. It is how much light is able to reach the surface of our planet. And I mentioned how in the UV we need to go to space to actually observe this kind of light. And that is because our atmosphere absorbs it and does all those photochemical effects that I was talking about. And the same is true for other planets. When we look at other planets, their atmospheres are also absorbing this light, and all of these photochemical reactions are occurring in there as well. For example, the example I gave of oxygen and ozone. And this probably is not super surprising to this audience, but not all stars are the same. I had shown this earlier. This is the spectrum of our sun. And then if I were to add onto it the spectra of other stars, you can see some key differences here. So along with our sun in black here, I have a spectrum in red. That is an M dwarf star. I have this orange one here. kind of orangish here, yeah. That is the star Epsilon Eridani. And then in the blue, we have an F-type star, which Orlando had mentioned before, Procyon. It's a star that's near and dear to my heart. I observed it with the Sistine sounding rocket in grad school and was able to actually create the spectrum that's here today using data from that mission. And you'll notice there's a big change in the near ultraviolet band, where these stars are outputting this stellar continuum at much different levels. And remember, these are on logarithmic scales, so the change between the blue and the red here is about 100 times. So these stars are seeing vastly different ultraviolet radiation environments, as well as X-rays. You can see there's an enhancement for these lower massed stars compared to the higher mass ones, like our sun. And this leads to some interesting effects. There were several studies in the mid-2010s that were trying to understand how these different types of stars can impact planets and their atmospheres. And so this plot on the right here tries to illustrate that. So along the vertical axis, we're seeing altitude within the atmosphere of an exoplanet. And then along the horizontal, we see this term we use that's called the mixing ratio. You can think of it as essentially how much oxygen is in your atmosphere, where to the left you have less oxygen, and to the right you have more oxygen. And an interesting thing that they found in this study was that for these higher mass sun-like stars and a bit larger than the sun, you don't end up actually getting any surface oxygen on the surfaces of these planets compared to these lower mass stars, these K and M type stars, which are able to accumulate oxygen. And that's all because of these photochemical reactions that are occurring. The reason we actually do have an appreciable amount of oxygen, represented by the green line here, is because we have, of course, life on our planet. We have lots of plants that are producing oxygen for us to breathe. It's very good that they're doing that. But if we were to look out to another planet, we have to be a little careful about if we see oxygen, whether that actually means it's a sign of life or not. Yes, and then there's highlighting those regions. Okay, so this animation probably will not play either, but if you can imagine, the sun here is emitting lots of XUV photons, that X-ray and extreme UV light that I mentioned before. This light at these energies is responsible for determining how puffy your atmosphere is. As you increase that XUV light, your atmosphere gets puffier. Let's see if that plays out. It might not. But essentially, as your XUV light comes, it increases, not only does your atmosphere get puffier, but it also gets hotter. Those photoionization reactions are happening and launching all of these really fast energetic electrons everywhere, and it's heating things up and puffing them out. And if this process occurs too much, you can actually end up losing your atmosphere over time. Okay, yeah, that sort of worked. If you imagine the molecules and atoms kind of drifting away over time, as you just blast atmospheres with extreme ultraviolet and X-ray radiation, you can cause a set of reactions that will actually end up having your atmosphere flow out of the gravitational pull of your planet, leaving no atmosphere behind. And as we said in the beginning of this talk, having an atmosphere is pretty good for us and potentially other life in the universe. So the story of photochemistry occurring in exoplanet atmospheres is not the beginning of that story, actually. This also occurs in protoplanetary disks, which I mentioned before, the birthplaces of planets like our own. So this is an example of what one of these looks like. You have a star here right in the center of the disk, and you have all this gas and dust surrounding the star, orbiting about this young star here. And you can see here there's the little specks. These are the seeds for new planets that are forming within this disk. And another study in the mid-late 2010s was looking at the impact, again, of different types of stars and how that impacts the structures of these disks. And there's a lot going on here, but the way to think about all of these individual plots here is that the central star is in the bottom left corner of all of these. And what we're looking at here is these two columns are less ultraviolet light, and then the ones immediately to the right are more ultraviolet light hitting those disks from their central star. And what we see is differences in these structures. For stars that are emitting less UV light, for example, they have a lot less methane available in the inner parts of the disk, whereas stars orbiting, planets orbiting stars around higher mass that are emitting more ultraviolet light actually have a lot of methane available for planet formation. This is an effect that actually will determine what your planets are made of before they even have an atmosphere. So photochemistry is happening all the time, and it has some pretty big implications onto habitability and complicates things a lot. Like I mentioned before, we have to be a little careful about when we see things, whether or not those are actually signs of life, or if nature has a way to produce that naturally. And just like exoplanet atmospheres that can be completely irradiated by this extreme light, this X-ray and extreme UV light, disks also evaporate over time. And depending on the type of star, they will evaporate at different locations and at different rates. That's what this plot is trying to illustrate here. These models up top are trying to show, for example, this EUV model, the distance from that star where you really start evaporating is much closer than if you include X-rays or compared to a star that's mainly outputting in the far ultraviolet, for example. So it's all interconnected. And the last thing I wanted to talk about today is how we actually observe this in space. I've shown you lots of different models for how we try to understand what these impacts are, but is that actually happening out in space? How do we know these things? And so we first look at the Atacama Large Millimeter and Submillimeter Array, or ALMA. This is an array of essentially radio telescopes that observe at wavelengths of 0.3 to 3.6 millimeters. So kind of essentially on the smallest of human scales. If you're more in radio, that's about 30 to 1,000 gigahertz, the frequencies that it observes at. And all of these individual dishes here are actually independently movable, and they can be moved around to a radius of, I believe, 15 kilometers to do this radio interferometry. There's 66 of them total. It observes at 5 kilometers above the sea level. That gets us high enough in the atmosphere that we have less atmospheric interference. It's at the top of a plateau in the desert, the Atacama Desert in Chile. And that allows for, again, better viewing, less water in the atmosphere. So it's a very high sensitivity instrument. Actually, it's the highest sensitivity in terms of spatial resolution at these wavelengths that we've built so far. It's been operating for about 13 years now. And in those 13 years, it's taken many, many beautiful images of protoplanetary disks with enough resolving power to actually make out some of these ring features that are being cleared by that photochemistry. So it's very interesting to look at. We have a large collection of these now with ALMA. And an example of photochemistry actually happening in disks is shown here. In this study in 2018, astronomers found a ring of cyanide within this protoplanetary disk. And this puzzled a lot of astronomers for a while. They were trying to figure out, well, how did that formation get into this disk? Where does it come from? How is it made? And they did a lot of modeling and kept ruling all of these models out. And ultimately, they determined the only plausible way for this formation to occur was through photochemistry. And they were able to figure out the chemical reactions that occurred to form this. The telescope that needs no introduction, but I'm going to give one anyways, the James Webb Space Telescope. This is, of course, NASA's more recent flagship missions that observes in red and infrared wavelengths, about 0.6 to 28.5 microns in wavelength. It consists of 4 different instruments: the mid-infrared instrument, near-infrared camera, or NIRCam, the near-infrared spectrograph, NIRSpec, and then this mouthful of an instrument name, NIRIS/the FGS. And all of these instruments are specialized to do different things with the James Webb Space Telescope's primary telescope mirrors that you see in gold. And it observes at a modest 1.5 million kilometers above sea level, just a bit further out than ALMA. And it's been operating for just over 4 years, launching on Christmas back in 2021. And again, in those 4 years, it's been doing a lot of really novel studies of exoplanet atmospheres, primarily through things like the transit method, where, of course, we have a planet that crosses in front of its star, blocks out some of that light, and then comes back off on the other side. And you'll see in this figure, it's a little hard to see, but you can see the red dots are a bit higher than the green dots, and that's representing light at different wavelengths being absorbed at different amounts, essentially. And that actually tells us about what is in the atmosphere and how much of it is in there. And again, if this story sounds a bit familiar to you, let me know. The first exoplanet to be studied with James Webb Space Telescope was WASP-39b, where they took these very beautiful infrared spectra. And they found features they were expecting, like water features here and here. It made the first ever detection of carbon dioxide in an exoplanet atmosphere. This was a feature predicted to be here, and they actually observed it for the first time. But then there's this weird little bump right here that they were not expecting to see. And that, again, puzzled astronomers. And they did a lot of modeling to try and figure out what it was. And ultimately, they learned that it is silicon dioxide. This plot that I had shown earlier is from this study. And for the first time, we've had observational evidence of photochemistry happening in a planet outside of our solar system. We had never actually seen these photochemical products before until we had the power of James Webb. And this was back in 2023 for a planet about, it's, I believe, the mass of Jupiter, but the size of Saturn. And this happened again just a few months ago. We have this exoplanet, HAT P26b. This is a Neptune-sized planet. And it was also found to have, there's that carbon dioxide feature, but it also has the silicon dioxide feature. So this is the second instance now of us observing this type of feature, again, because of photochemistry, altering the atmosphere of that planet. So I mentioned Jupiter, Saturn massed, Neptune massed. What about Earth-sized? That's kind of the next frontier in space telescopes. This is a concept image of what the Habitable Worlds Observatory might look like. This is highly subject to change. And it's actively being studied right now what this thing is actually going to look like. It most likely will observe far ultraviolet to near-infrared wavelengths. Essentially, you can think of it as the coverage of the Hubble Space Telescope in wavelength space, but with a design more similar to the James Webb Space Telescope with the big hexagonal mirror segments. Its telescope design, as I mentioned, is being worked on right now, determining things like what instruments it's going to have, what wavelength regimes are they going to be looking at, as well as what actual science it's going to do. Despite the name being Habitable Worlds, it will study other things aside from habitable worlds. This is another big flagship mission that NASA is going to be building. And it has to, as I said before, do everything essentially in astronomy. It just has this habitable worlds kind of driving a lot of that. And it's expected, as of right now, to launch in the 2040s. That is subject to change, of course. It might slip into the 2050s. But right now, everyone's working off launching in about, I think 2045 is right now the predicted launch date. And it's going to dedicate a significant amount of observing time to study 100 nearby star systems away in the neighborhood of our solar system. And with our most recent models of where we expect habitable planets to be, based on the literal thousands of exoplanets we've been studying in the past 30 years, we're anticipating about a quarter of those star systems will have what we call an exo-Earth, or a habitable Earth-like planet in the habitable zones of these stars that are about the size of the sun, or a bit bigger, or a little smaller. And it does this through transmission spectroscopy, like James Webb does, but also will do this through direct imaging, like ALMA and JWST have been doing recently. And here's examples of that here. So on the top, we have the transmission spectra of our planet, the Earth, and all of its intricate little features that make the Earth special compared to other exoplanet atmospheres, or maybe it's not as special, and there actually are lots of worlds that look like this. But whereas James Webb primarily looks in this infrared region, we'll also be pushing into the ultraviolet region and studying the atmospheres of these planets in the UV. And you'll see features like ozone bands and oxygen and other things like that. And direct imaging. So this is a concept image for the Habitable Worlds Observatory. It will be the first space telescope to actually take direct images of habitable zone planets. We have been able to image planets with instruments on the James Webb Space Telescope, but those have been much further out. Think like the orbit of Neptune and beyond. Not really super close to the habitable zone. So that's kind of the next frontier in our capabilities with space telescopes. So with that, I hope you enjoyed the talk. I'm happy to take questions. Thank you.
How can you actually tell what those chemicals are that far away?
Lots and lots of modeling. So astronomers, when they build these photochemical models, they literally have networks of chemical reactions that are occurring. And the way we know that these are occurring is lots of laboratory experiments here on Earth. We are in lab environments setting up conditions that we think are happening in these exoplanet atmospheres and seeing what chemistry is arising as we illuminate it with these different types of wavelengths.
So you're comparing it to something that's been performed.
Yes.
Okay.
There is a little bit of theoretical work as well because we can't simulate every environment, but that is one of the ways that we know that these processes can happen in the right conditions and are potentially happening in these atmospheres. Yes?
Now, you're measuring the emission spectroscopy, and that tells you what the chemicals are?
Yes, the question was if we're observing with emission spectroscopy, and that tells us where chemicals are in these atmospheres. Yes. By observing these emission features in the spectra of these planets, we get a sense of what is being emitted. Every atom or molecule will have its little spectroscopic fingerprint. It only emits at certain wavelengths, and we were able to predict that using quantum mechanics, essentially. And that allows us to know, okay, if we see a feature in this region, it could be things that we've seen in laboratory experiments, for example. Yes?
Did I hear you right? You said that the polar regions of stars rotate faster?
The question was if the polar regions rotate faster. It's the
Supermassive stars?
I'm not familiar enough to say for sure, but the low mass stars, spectral types F and lower, the way their internal structure is causes this. Yeah. Yes.
So with this, you can pretty much look at the type of star and then kind of make predictions on what you would find with the planets. So you kind of know, like, oh, we can look at this star with a higher probability of finding X, Y, Z.
Right. Yeah. So. World's instrument. We want to be able to do research now that informs them of, okay, we don't want to look at this F-type star, for example. It has way too much radiation. It's most likely that planets in the habitable zone around that star are not going to have atmospheres to even look at. So there's studies like this that are happening now to determine which of those 100 stars we're actually going to observe. Yeah. All right.
Very good. Well, thank you, sir. We appreciate it. As is customary for all of our speakers, we have new for 2025 same spirit, but a slightly different model of a mug with some of the imaging from one of our club members.
Wonderful.
And then your name and our logo. So thank you very
Thank
much.
you so
We
much.
appreciate you for coming out and bearing with our technology. You're a professional with that. So
If anyone wants to see the animations, let me know.
right. Excellent. But thank you very much. Appreciate it.
Thank you so much. And I left the mic here.
Alrighty, well with that, that pretty much wraps it up. I do want to make sure that folks know that we will be having a board meeting in February and all members are welcome to attend that. We want to make sure that that is kind of those meetings where things are decided, any changes, any programming. So if there's something that you've got an idea, you're certainly welcome to send that to us and we can discuss it, but you're more than welcome to come out and participate as well. So that's taking place on the 4th. That will be popping up on the website here in a day or two. I kind of